So we've got a bunch of content today that's not going to presuppose any prior knowledge. My talk is going to presuppose a little bit of prior knowledge. So this is a 201 level talk. If you feel a little bit lost, that's okay. We'll go back to the basics for Steve's introduction talk and some of the other content today. But I'm going to assume a little bit here. So just to level set, my talk is on cloud databases, and when I'm definitely most interested in building applications and the databases that run those applications. So I'm talking about the operational databases category, not the analytical category. And in particular, with cloud applications, you need a database that can scale out. So I'm talking about the upper right corner of this group. So when you look at cloud databases today, there's kind of four big names, I think, that most people will think of. So you've got DynamoDB from Amazon, Cosmos DB from Microsoft, Cloud Spanner from Google, and Apache Cassandra. So of these four databases, they've come out at different times. Amanda told you Cassandra was open sourced in 2008. DynamoDB came out in 2012, and the others came out more recently. But there's some stuff that all of these products and all of the engineers working on them agree on. So one of those is that eventual consistency is useful. So this is another term that Amanda threw at you, and that means that it's okay for not all replicas to have the most recent data at the same time. And why is that okay? I'll show you in just a second. There's something called the CAP theorem that says that you can't have all three of consistency, availability, and partition tolerance. And this is consistency in the sense of, like I said, everyone agreeing on the same data at the same time. So it's a different C than the C in ACID. So when you're thinking in terms of CAP theorem and you're thinking in terms of a database and you're evaluating it and asking what kind of database is it, one of the questions you want to ask is what happens if a node goes down? If it's an HDFS name node, then you lose access to your data. So that's an example of a system that's what you would call a CP system. It's designed for consistency over availability. So if one of those nodes goes down, then I might not have access if it's the wrong node. So if the name node goes down, I'm going to have to wait for failover to a different name node, a backup name node if you have one, before I can do more requests. But if it's an AP system, a system that emphasizes availability, we say, hey, that's no problem. Just get your data from the copy over there, and it might be a few milliseconds out of date, but that's cool. That's what we're OK with. So what a lot of people don't realize at first is that most of the databases that you use are built around some form of eventual consistency. And so even if I have a database that's built around master-slave replication, which is kind of the standard CP world, I will have eventual consistency if I read records from one of the replicas rather than directly from the master, because I'm doing asynchronous replication between the two. So if I'm moving to an AP system, the difference is now those replicas, now they can accept writes as well as reads, and we'll do bidirectional asynchronous replication. So it's my opinion that for the vast majority of cloud applications, this AP design is a better one because you don't have that single point of failure that you need to worry about failover for, and you're doing a better job of scaling your writes because any node in the cluster can accept those writes and forward them on to the correct replicas. So if we look at these cloud databases, Cassandra defaults to eventual consistency. Dynamo and Cosmos DB also default to eventual consistency. The odd database out here is Spanner, which is a strictly ACID database, does not support eventual consistency. Another thing that almost everyone agrees on is that automatic partitioning doesn't work. And so there was a research system called HStore back in 2012. And what they said was, hey, these distributed databases like Cassandra, these are cool, but it's really hard for developers to have to think about partition keys, which we'll be covering in data modeling. And I wish we didn't have to expose that level of detail to users? Wouldn't it be nice if we could just keep writing SQL and not have to care about, now you're in a distributed system? And so a bunch of researchers, their names are on this slide, wrote this paper about how they did automatic partitioning for this HStore database. And it worked as designed. So this isn't a case where they had a good idea, but they couldn't make it work. They made it work. What you did was you told it, here's my tables, and then here's my stored procedures that I'm going to use to access those tables. And by analyzing the stored procedures, I can tell which pieces of data get accessed together, and I can put those pieces of data on the same partition. The problem is that there's no partitioning that will always give you that characteristic, that you'll be able to access data together in the same partition. You have to make compromises. You have to say that, even though I want threads and comments most of the time, sometimes I want comments by user as well. And in that case, since I'm optimizing for comments by thread, the comments by user will be less efficient because those aren't co-partitioned. So we won't be able to come up with a partitioning that satisfies everyone. We have to pick which queries are going to be slower. And the problem is that with this automatic design, it was even more confusing to users than having to deal with the partitioning up front, because when you are telling the system how to partition it, then you understand why some of those queries are slower. It's because you partitioned it a different way. But when the database is doing the partitioning and doesn't tell you, then it's a lot harder to understand. So all of these 4 databases have standardized on, we're going to let the user tell us how he wants it partitioned, and just live with that compromise. The third thing that almost everyone agrees on is that SQL is actually a pretty good language. So this kind of started off as kind of the NoSQL database wave, but people have come around to actually SQL is pretty good. Does anyone remember CouchDB? A couple people, yeah. So this was inspired by CouchDB. Yeah, so there's some things that are less, SQL is not the most user-friendly language in the world, but there are things that are less user-friendly. And so the world we've ended up in is that everyone's kind of accepted that, and Cassandra was the first in 2011. We released CQL, and CQL 3 is where it really became useful. Pretty heavily inspired by SQL. And then you've got Cosmos DB and Spanner. They're actually saying that they're SQL databases. They're dialects of SQL in the same way that CQL is. And then you've got DynamoDB. Again, this is the category of stuff that almost everyone agrees on. DynamoDB is still with a key value API. If I were to make a prediction, I would predict that within 2 years, DynamoDB will join the rest of the world with a SQL API, or a SQL-ish API. And that's about it. That in terms of when I look at these things, what does everyone agree on? That's about it. So the next category is stuff that we don't agree on, but I'm going to explain why I'm right. So one of those things is that Schema is good. There's a bunch of databases out there. Cosmos DB is one that says, hey, we're going to be schema-free. You just throw whatever data you want into the database, and we'll figure out a way to index it and give that back to you when you ask for it. But the reason that I claim that Schema is good is that when you have a successful data-oriented project, you start off with, maybe I have a set of Python web pages that access that data. But as that project becomes more successful and gets more customers, then you start getting a bunch of things like GitHub actually. Started as a great example. Started off as a Ruby on Rails shop. They just gave a talk at Oracle Open World about how their data pipeline is all based on Java, because it's just more performant. It's a great sweet spot between performance and productivity. Maybe you have some super performance critical pieces that you have a team write those in C++, all accessing the same data. Maybe you've got some Ruby on Rails people like GitHub. And so you start to have lots of different teams, and they're each selecting what they think is the right tool for the job, and they all want to share that same data. And that's where having that schema is a useful thing, because it makes sure that all of those teams have some common structure that they agree on. Twitter actually wrote a research paper about their experience with schemaless JSON documents. And one of the problems that they ran into is that these different teams would actually structure documents in a subtly different way. And the example they gave was with user IDs. So one of the teams had user IDs that were numeric but represented as a string. Another team had user IDs that were numeric represented as an integer. And the third team had user IDs with an underscore. And so all of these work fine as long as only the code base that wrote that data is reading from it. But as soon as you have a Spark job that's trying to go through all of those pieces of data, now you have to you have to de-garbage that in your Spark job instead of keeping your data clean in the first place. So I claim that schema is a good thing. Got some company in this cloud database world. Cloud Spanner also agrees. We're going to make schema mandatory. DynamoDB is kind of on the fence. It's schema optional. You can specify data types, but they're optional. And then Cosmos DB, like I said, is completely schema free. And then the other main point of difference is in the data model, where everyone's got their own slightly different take on here. I would say that the main common thread is that you're looking for ways to allow the user to have related pieces of data together. So one of the ways that DataStax and Cassandra do that is by allowing you to nest pieces of data in your tables. So you have collections. A column can be not just a primitive, but it could be a collection, or it could be a user-defined type with different levels of nesting. Spanner takes a different approach with parent and child relationships, where a child table shares part of the primary key of its parent, and those will be on the same machines. So there's the idea is that when you have your data spread across lots of machines, you want a way to say common data should be accessed together. I have another talk that's online where I go into more details about the differences between these systems. So if you Google for Jonathan Ellis, Cassandra, and the cloud, you'll get the slides. And then I also gave a talk at Strata that's where the video is available as well. So what I want to talk about for the rest of my time here is some practical considerations. Like if I'm thinking about spending money on one of these databases, what should I know? So it's difficult to compare these different systems because they all have different data models and they all have different APIs. But Cosmos DB actually made it much easier to do a comparison. A couple months ago, they released a Cassandra compatibility API for Cosmos DB. And so we said, hey, we know how to benchmark Cassandra. So we're going to do a comparison. And we based this comparison on one that we commissioned from a company called ZData. And basically what this is saying on the right here is that this is a time series schema where we have we have a million sensors, and they're all generating data points that have a timestamp associated with them and a data payload. And so that's the schema that we're working with. So we did 3 scenarios. We benchmarked 3 scenarios. One where we're varying the percentage of writes versus reads. So the first one is 10% writes, 90% reads, and then bottom one is the inverse, and then the middle one's 50-50. And so we priced that out, and we actually scaled up the cluster to the Cosmos DB thinks of this in terms of request units. How much is it going to cost for a Cosmos DB database to match the performance of a 5-node DSE cluster running in Microsoft Azure. So that's what we did here. So we found that the Cosmos DB was going to be between 2.5 and almost 10 times as expensive to get that performance. So yeah, there's definitely a level of convenience there where Cosmos DB is handling all the operations, but you're definitely paying for it as well. The other thing we looked at was, okay, that's the throughput, but what does the latency look like? So what we did here is, I'll point out that on the left, this is a log-scaled graph. So every line there, we're going an order of magnitude from 10 to 100 and to 1,000. And so here, down at the bottom, this is what Cosmos DB publishes as their SLA. And they say, we're going to guarantee that 99% of operations finish in less than this amount. And so what we did was, so we took the level of throughput that we're benchmarking here, and we said, what does the latency look like when we start with 20% of that throughput and go up to 80% of it? And so you can see that what we have here is the purple and the teal. These are DSE's lines. And then you've got the orange and the slightly different orange that are Cosmos DB lines. And I apologize. For anyone in the audience who's colorblind like me, I apologize. Those are probably bad colors to choose. But you can see that we're blowing way past the SLA. The bad news for DataStax fans is DataStax isn't doing a whole lot better. It's a little bit lower, but not a whole lot better. And in fact, Cosmos DB is actually doing a lot better on the read latency in particular before we hit that 80% level when it just kind of falls apart a little bit. So that's the latency story, but this is the rest of the latency story. So we also benchmarked it with the new ZGC garbage collector that's out in Java 11. And so these are the new DSE numbers with Java 11. You can see that we're doing, again, this is log scaled. So we're doing roughly an order of magnitude, almost 2 orders of magnitude better on the 99th percentile, and doing significantly better on not just the 80%, but also all the other levels of workload that we're throwing at it. If you're not familiar with Java garbage collection algorithms, a great talk introducing ZGC from the author that you can Google. But the short version is that it optimizes for much shorter pauses at the expense of using a little more CPU. So what this graph tells us is that most of the 99th percentile pauses that you get with DSE today are the result of the Java garbage collector and not the result of DSE itself. And when you address that with a better garbage collector, and by the way, Azul Zing is another option besides ZGC, and they'll be happy to sell that to you today. So you can make those latencies get much better with DSE. One more point about the latency that we saw with Cosmos DB. It wasn't really a normal curve. So it wasn't really like, here's the most common latency, and then you've got, it kind of gets less common as you get away from that most common one. It's really more of a bimodal, where you either have, right around meeting the SLA of around 10, or you have it at about 1,000. So those are definitely the most common. You get a couple outliers, but it was more of a bimodal distribution, which was a little surprising. So DynamoDB, we can't benchmark it directly. There's no Cassandra API. But if we go by what their documentation suggests and their pricing that they publish, it's about 20% more expensive than Cosmos DB. And it's significantly weaker in terms of the data model, which again is key value based, and the other features that it provides. Spanner, I don't have a head-to-head comparison with Cassandra, but I do have a comparison that someone from Cloudera did against a database called Kudu. And the interesting thing about this is Kudu shares a lot of architectural things in common with Cassandra. So I would expect that on the load throughput in particular, that Cassandra would do similarly to Kudu, to 50 to 100% better. And I would expect Cassandra to do significantly better on the reads because Kudu is optimized for analytical scans rather than the point queries that this benchmark is testing. But this is what they found, which is that Spanner just really, again, I kind of glossed over it earlier, but Spanner is optimized for all ACID all the time. And that means that in a distributed system, you give up a lot of performance to get that. And that's visible here. So the last thing I want to point out is that when you're talking about a cloud database, write once, run anywhere, that was Java's tagline for a while. And I think it's an important thing to think about when you're talking about where am I going to deploy my application and what infrastructure is it going to run on. So you've got a bunch of industry analysts saying that there's an increasing awareness that hybrid cloud is more and more important, and it's not enough to just have a database that runs on one cloud and nowhere else. Gartner had a useful way of thinking about hybrid cloud that they divided it into 4 categories, where the first one is architecture spanning, where you actually have, this diagram is trying to say that I have a single database that's spanning from an on-premises deployment and into the cloud. And Cassandra is one of the few databases that can do that. But then the other ones are variations on, I have some data on-premise and some data in the cloud, and they don't necessarily need to replicate to each other, but it's good to have a common interface so that I'm not, I don't have to write my application one way on-premise and a different way for the cloud. And this is what DataStax is seeing as well. We're seeing roughly 63% of our customers running applications in the cloud, and those are a subset of the 100% that have applications running on-premise as well. So yeah, we agree that this is the future. So my takeaway from that is, I wouldn't want to be locked into a database that only runs on one cloud. I want the flexibility to deploy that on-premise. I want the flexibility to, if my company acquires someone who's using a different cloud, I want to be able to have a data layer that I can have in common between those. So DataStax, besides running, selling licenses that you can run on premises, we also have DataStax Managed Cloud. We'll run DataStax for you on the cloud of your choice. And so my recommendations are, first, that I would never recommend DynamoDB. The feature set is just too limiting. The data model is not as productive. You will not write your application as fast. And Spanner is just too slow and too expensive for what you get. Now, that price of ACID in a distributed system is very high. Cosmos DB, I've got a lot of respect for what they built. It's a good system. It does get expensive as you scale it. And then, of course, my bias, I'm the founder of DataStax, but I think I think I've made a pretty good case for why DataStax Enterprise makes a good set of trade-offs as a cloud database. My final thought, I don't have time for questions this morning, but feel free to catch me around in the halls. But we are hiring. If you like thinking about distributed systems, then reach out, unless you're a DataStax customer, in which case, forget I said anything. Your boss will be upset with me. But if you're not a DataStax customer and this kind of stuff excites you, then let's talk. Thank you.